However, we're fortunate enough to have the star of this DVD here to give us a live lecture.
Okay. Well, thank you very much. So this should have been the lecture on Monday morning. So this is by far the most elementary lecture that you'll hear. It's aimed at non-mathematicians or those who have maybe an undergraduate background in math. So if you've recently studied algebra at a graduate level or algebraic geometry, this would be a very good moment to leave. Now, if you're planning to do email or look at your screen during the next 58 minutes, this would be an excellent moment to leave. So I have a personal favor to ask you guys over there to either go and do email outside and look at those great pictures outside, or maybe close the laptop. Do you think you could do that? Gentleman with the shirt. I really don't mind. You can leave any time during the lecture because this is something that you've seen many times. But I think it's actually very nice for the speaker to people not to look at the laptop. So Gröbner bases are a method for computing with polynomials in several variables, multivariate polynomials. And they generalize three well-known algorithms. So well-known if you've studied math at an undergraduate level. So the first one is Gaussian elimination for solving linear systems of equations in many unknowns. Euclidean algorithm for computing the greatest common divisor. So you're familiar with this for computing the greatest common divisor of integers, but works just the same for polynomials in one variable. And it also extends, as I'll explain, the Simplex algorithm for linear programming. Linear programming is the problem of solving linear systems of equations and inequalities over the reals. So the general setup is that we have a collection of input polynomials, f1 up f2 up to fn, and they're going to be brown. So we have some bunch of polynomials, brown polynomials f. We feed that to some algorithm, Buchberger's algorithm, and the output will be a set of output polynomials, blue g, g1, g2 up to gm. And the point is somehow that information about the input, brown f, should be easier to understand by inspecting the output, blue g. Okay, so we think about this as a general purpose tool. You feed a bunch of brown polynomials, lots of things happen, out comes a bunch of blue polynomials, and by looking at the blue output, you can answer questions about the brown input. So example, Gaussian elimination. So suppose we have a system of two linear equations in three unknowns, x, y, and z. So here they are, 2x plus 3y plus 4z equals 5, and 3x, plus 4y plus 5z is 2. So this is a system of linear algebraic equations, and let's feed them to some machine, and out comes a perfectly equivalent system of equations, which says x equals z minus 14 and y equals 11 minus 2z. So we think about the input as the problem, and after the arrow, we think about that as the solution. So we've learned information. We've learned that this has a one-dimensional solution space. The solution is a line, right? So this system of equations has infinitely many solutions. They form a line in three-dimensional space with coordinates x, y, and z. And here's sort of in Gröbner bases notation, right? So brown f is a system of polynomials. I just take this right-hand side, the equal 5 as a minus 5. So this lecture is really for you, Mary Lee. This is for biologists. So we've taken the 5 of the other side. So we have these brown polynomials. Then we do something, right, that we learn in output, is x minus z plus 14 and y plus 2z minus 11. Notice that I underline the x and the y. So that sort of shows that in the final output, x and y are the dependent unknowns, and z is the independent. Z sort of parameterizes the line. We have this entire solution of, entire line worth of solutions that gets parameterized by the unknown z, And then x and y are given by a simple expression in terms of those. So we've made progress by going from the brown input to the blue output. Here's the Euclidean algorithm. So the Euclidean algorithm computes the greatest common divisor of two polynomials in one variable. So here I have two brown polynomials, so polynomial of degree 4, x to the 4th minus 12x cubed, blah, blah, plus 4. And another polynomial of degree 5, x to the 5th minus 5x to the 4th plus 5x cubed plus 5x squared minus 6x. So the greatest common divisor is a polynomial that divides both of them and has all other divisors as a factor. And that unique polynomial up to scaling is x squared minus 3x plus 2. In Gröbner Bases notation, we have a set F of two equations, two polynomials, non-linear polynomials in one variable x, and output is a set G. So this process, the division algorithm, the Euclidean algorithm, takes this brown input and produces a single polynomial, x squared minus 3x plus 2. Now, another way to think about this is if you want to find the common roots of the two blue polynomials, then we've learned by this process that x equals 1 and x equals 2 are the common roots of the two blue polynomials, right? Because the two brown polynomials, right? Because this blue polynomial is x minus 1 times x minus 2. It visibly has 1 and 2 as its roots, and therefore those are the common roots of the two brown polynomials. So we've learned something about the inputs. If the question is, what are the common roots of the two brown polynomials, then the output reveals it to us. And if the output had been 1, then we would have learned that the two brown polynomials would not have had any common roots together. So the Euclidean algorithm is an algorithm that eats linear polynomials in many variables and solves them somehow. And the Euclidean algorithm is an algorithm that eats several polynomials of high degree in one variable and produces an output, a solution. So, well, wouldn't it be nice if we had a common generalization? Wouldn't it be nice if we had a Euclidean algorithm that could take nonlinear polynomials in many variables? And wouldn't it be nice if we had Gaussian elimination for nonlinear equations? And the answer is yes, of course, that's Gröbner Bases. Let's do an integer programming example. So I talked about linear programming, and here I'm going to require that the unknowns are actually integers. So let's look at the following problem. We like to minimize the linear function in 4 unknowns, p plus n plus d plus q, subject to one equation, p plus 5n plus 10d plus 25q equals 117, where these unknowns, p, n, d, and q, are non-negative, but I also like them to be integer. Okay, so this is some optimization problem. Turns out that this optimization problem has a unique solution. P is 2, n is 1, d is 1, and q is 4. Okay? Now, that's an example of an integer linear programming problem. Now, what's the meaning of this? This is P for pennies, N for nickels, D for dimes, and Q for quarters. So these are the coins in the US currency system. And this problem in English is to express $1.17 with the fewest coins possible. Okay, so what is the fewest? So the sum P plus N plus D plus Q, that's the number of coins. And the second equation says the monetary value of these coins is $1.17. And we like to do that with as few coins as possible. And the solution is there's a unique solution using 8 coins. So you cannot do it with 7 or fewer. You need at least 8 coins. And the unique optimal solution is 2 pennies, 1 nickel, 1 dime, and 4 quarters. And that's an example and sort of characteristic example of an integer linear programming problem. Now, integer, because these coins are indivisible goods, right? So coins, this kind of situation, of course, if we did not have divisibility, if we allowed fractional coins, we could do better, right? Then we could say P and N and D are 0, and Q is 117 over 25, which is about 6.5. Right? So a better solution would be even less. I think it's about 4.5. Right? So we could certainly do it in 4.5 quarters. But that would mean, cutting coins, and that's not legal. So if you cut the coin, you walk into a store, they won't accept it. So therefore, we need to do this using integer linear program rather than linear program. Question? Of course. All interesting problems are NP-complete.
So is there any...
No. So I'm not going to present an efficient algorithm in the sense of complexity. Okay. So I'm presenting an approach of thinking about integer linear programming problems. Now, actually, it's not so bad. Let me say one sentence with the complexity hat. So if the number of variables is fixed, but the size of the integers grows big, then there is a polynomial time algorithm, and that gets mirrored by this method. And it tends to perform well in this situation. So for me, an integer, so for most people in computer science, there are only two integers, right? 0 and 1. So that's not an integer programming problem for me. So for me, when I say an integer, I mean like 117. That's an integer for me. So if these integers go big, then this tends to perform well. Meaning polynomial time if the number of variables is fixed. But I haven't explained the method yet. I mean, what on earth does this have to do with Gröbner bases? We haven't even gotten to polynomials yet. So let's get to polynomials. Let's represent a collection of coins by a monomial. So a current, collection of coins, a bag of coins that you might carry, let's call that a portfolio. So portfolio might consist of A pennies, B nickels, C dimes, and D quarters, and your goal is to optimize your portfolio to, have the fewest coins that you have to carry around or some other objective function. So for instance, the monomial, we're going to represent such a portfolio by a monomial. So P to the A, N to the B, D to the C, Q to the D represents this. So for instance, P squared D to the 4th represents a bag with 2 pennies and 4 dimes. So now I have to phrase this as a Brown set of input polynomials producing some output polynomials. So the Brown set of input polynomials specifies equations that gives equations that specify the monetary relationships among these coins. So the input set F is P to the 5th minus N. Well, that says that 5 pennies are a nickel. P to the 10 minus D, that says 10 pennies are a dime. P to the 25th minus Q, that says 25 pennies are a quarter. So that I'm specifying. So now the output set is some blue set of polynomials that are also true relations, and P to the 5th minus N, N squared minus D, D squared N minus Q, right? 2 dimes and a nickel is a quarter. And finally, D cubed minus NQ, 3 dimes has the same values as a nickel and a quarter, namely 30 cents. So the way I interpret these is as replacement rules. So the expression D cubed minus NQ translates in English to replace 3 dimes with a nickel and a quarter. Now, why is this a good thing to do? Well, that maintains the monetary value while making progress towards minimizing the objective function. Keep in mind, you want to minimize the number of coins you're carrying around. So if in your pocket you replace 3 dimes by a nickel and a quarter, you made progress. You stayed feasible, but you made progress, right? Okay. So what's the point? The point is, given any collection C of coins, we can use the rules encoded by the set G, by the Gröbner bases, to transform in any order any set of coins. So we can transform the input into a set of coins C prime with equal monetary value but smaller number of elements. So for example, right, so we might have some feasible solution. Currently we have 32 coins, P to the 17th, N to the 10th, D to the 5th. So now we say let's trade 5 of our pennies for For nickel, right, p to the 12th, n to the 11th, d to the 5th, we do that 2 more times. Now we're stuck, right? Now we have p squared n to the 13th, d to the 5th. So now we have to call this the next rule that says you can replace an n squared by a d, and you keep going for a while. And on my computer, we get the final solution, but on Lior's computer, we don't. So that's how it goes. So basically, you know, you take these polynomials, these monomials, whenever you can apply a rule, you do. And at some point, you get stuck. And you get stuck at p squared n times d times q to the 4th. At that point, you can no longer apply any of the improvement steps. And at this point, we can actually conclude that we're at an optimal solution. So the Gröbner basis gives a method of transforming a feasible solution using local moves into a global optimum. So we perform these rules in any order until we can't apply them anymore. And then the blue set is so good, that it guarantees that no matter which bag of coins we started with, will be optimal. Okay? Now that is reminiscent, of course, of the Simplex algorithm for linear programming, which takes you from vertex to vertex of the feasible polyhedron along specified exchange steps. And then if you're at some situation where you can no longer apply a basis exchange, then that local optimum is in fact the global optimum. That's how the Simplex algorithm works. Okay? So of course, the trick is to find this blue set G. So G, again, this set G has the property, it's the unique minimal set of exchange rules that will work in this sense correctly for any bag of coins. Now that changes, right? You might travel to a different country, right? So maybe these numbers, 5, 10, 25, they will change. There will be another blue Gröbner basis with the same property, but it will be bigger and more complicated, and you can try it out tonight. In fact, if I didn't ask you to close your laptop, you could have tried it right now, but thanks a lot for doing it. So let's say, for the sake of argument, you travel to a foreign land, right? Hogwarts, for instance, you know. So this is going to be a bit more complicated at Hogwarts, right? So at Hogwarts, right, 1 galleon is, whatever, 19, sickles, and 1 sickle is 13 knuts, right? So then you can imagine that this Gröbner basis computation gets more complicated, but at the end of the day, there will be some blue set of transformation relations that enjoys the same property. Any questions? So I didn't speak about complexity. Any questions? Okay, so here's the theory. Okay, here's the theory. So in general, we're given a set F of polynomials in n unknowns, x1 up to xn, and the coefficients are in some field. Okay, so a field K for me, really sorry guys, a field K for me is like the rational numbers, the real numbers, the complex numbers. I'm kind of a characteristic 0 guy. So, 1 plus 1 being 0 is a little hard to take, but I know, for you, the last 10 days, 1 plus 1 has been 0, but let's say we work over these fields where 1 plus 1 isn't 0. In fact, I'm going to work primarily over the rational numbers. I don't really believe in the real numbers, right? Because I can't write them down, right? I cannot, let alone the complex number. I can't write down a complex number, right? You can't write down a complex number either, right? I can write down a rational number. I can write down any algebraic number. I can write down any number that's in a finite extension over Q, but I can't write down a real number, and you can't either. What you can do is you can write down a floating point approximation to some digit of accuracy, but at the end of the day, you're going to write down a rational number. Let's face it. So let's stick in the input to rational numbers. So the ideal generated by a set of polynomials Brown F is the set of all linear combinations with polynomial coefficients. So P1F1 plus plus PRFI, FR, where the FI are in the given set, and the PI are arbitrary polynomial multipliers. So such a thing is a subset of polynomials, and we call that an ideal. Now, the term ideal actually comes from ideal numbers. So this was sort of coined in a number theoretic sense. People talked about ideals. Ideals for rings play the same role as subvector spaces for vector spaces, normal subgroups for groups, you know. So those are the things you can mod out and pass to a quotient structure. That's the role of an ideal. Okay? Hilbert's basis theorem says that every ideal in a polynomial ring is finitely generated. So abstractly, an ideal is just a subset of polynomials that's closed under addition and multiplication by other polynomials, right? So, you know, merely, if you want to be an ideal, right, then what? Then you have to be closed. So any two polynomials in U, if you add them up or multiply, they're still in the set. Or you can multiply by some arbitrary polynomial that's still in the set. So that's abstractly an ideal. And this theorem says that if you're an ideal, then there exists a finite list of polynomials, Brown F1 up to Fr, that generates these in this sense, that it's already, every polynomial is a linear combination of those finitely many ones. So this was proved by Hilbert in a paper in 1890. Now, for one variables, you knew this all along, right? Because every ideal in a polynomial ring in one variable not only is finitely generated, but it's in fact generated by a single polynomial, right? So a polynomial ring in one variable is a principal ideal domain, right? So every ideal is generated by one polynomial in one variable, and that's called the Euclidean algorithm. So the Euclidean algorithm certifies this fact for you. It takes any bag of polynomials in one variable and replaces it by a single polynomial that generates the same ideal. Now, as soon as you're in two or more variables, that's just not true, right? There is no Euclidean algorithm for polynomials in two variables because ideals are not generated by one polynomial in general, not even by 2 or 3 or 7, but by some finite number. We don't know a priori how many. Right? Here are some examples of ideals. So in the examples that we've seen, the input set Brown F and the output set blue G were equivalent in the sense that they generate the same ideal. So in the Gaussian elimination example, I had these two linear polynomials in x, y, and z, and they generate the same ideal. Their set of polynomial consequences is identical to the polynomial consequences of blue x minus z plus 14 and y plus z minus 11. So in that sense, the brown input and the blue output are identical. They have the same polynomial consequences, but looking at the blue set is more informative, right? It tells you more about the solutions or something. Same in the second example, right? The quartic and the degree 5 polynomial together generate the same ideal as x squared minus 3x plus 2. And in the coin example, right, the input was the specification of the monetary relations, and the output are the trading rules. And these sets are equivalent in the sense that they generate the same ideal. So in each example, the polynomial consequences are the same, but the elements of G reveal more information, more structure than those of F. Now you can already see in this case, sometimes, you know, the size goes up, sometimes the size goes down, you know. But in each case, there's some advantage to the blue stuff over the brown stuff. And I'm really, really happy when I see people fall asleep because that means that they're really familiar with this material, which they should. So how do you check that two sets of polynomials generate the same ideal? How do you check that brown F and blue G generate the same ideal? Well, I need to show that every element in Brown F is a linear combination of the guys in G, and conversely, that every element in G is a linear combination of F. So, example, right? So, let me prove to you that 3 dimes is the same as a nickel and a quarter. Suppose you didn't know that yet, right? So, and speaking to a logician, so here's a proof, okay, that 3 dimes is the same as a nickel and a quarter. I'm taking the output polynomial d cubed minus nq, and I'm writing it as a polynomial linear combination of the input polynomials, the Brown polynomials that specify in the monetary system, and you're convinced, right? All you need to do is multiply out the right-hand side, so whenever the brown things are true, then the blue things follow. Excellent. So we need one more ingredient. Well, see, in one variable, how do you write down a polynomial, right? So typically you write down a polynomial, the highest term, and then the next highest term, and so on. But that's not so clear if you have 2 or more variables. So you need a systematic way of writing down polynomials, either on paper or on the computer screen. So such a systematic way is called a term order monomial order. So a term order is a total ordering on the set of all monomials, x1 to the a1, x2 to the a2, xn to the an, which is multiplicative. So if Lior and I are monomials, right? So, and I'm smaller than Lior, then that relationship will be maintained if we get multiplied by Reinhard. Okay? So that's means to be multiplicative. And there's a one loser, and that's the constant monomial. So the monomial 1, also known as x to the 0, is the unique smallest monomial. So the constant monomial. So these 2 rules specify a term order, and there are many, many, uncountably many choices of such term orders if there's more than one variable. So in one variable, of course, there's only one term order, right? So because if 1 is the smallest, so 1 is less than x. But if 1 is less than x, we can multiply them both by x, right? So x is less than x squared. Okay, so 1 is less than x, and x is less than x squared. So now we can multiply them by x again, so there's only one order, okay? But, for n equals 2, there are many orderings, including the degree lexicographic order and the purely lexicographic order. So those are sort of important to contemplate. So the purely lexicographic order, that's the dictionary order, right? So in the dictionary order, written as monomials, there's x2 is so much higher than x1 that as soon as x2 appears, it dominates, right? So, if you have a word that has an a in the beginning, right, no matter how many a's it has or how long it is, it's going to come before, a word that has no a in it, right, or that has no. So that's the dictionary order. But that does not respect the length. That does not respect the total degree. Now, you could imagine having a dictionary that respects it, where you first list the short words, and then you list the longer words, and finally you list the longest words, right? That you could imagine that, in fact, makes sense, right? In genomics, when you work with motifs and look up motifs and so on, then it makes perfect sense to have such an order. But in the usual dictionary you don't, then these are 2 choices. There's also the reverse lexicographic order. So that's the ultimate test whether you've understood Gröbner bases. If you know the difference between the degree lexicographic order and the degree reverse lexicographic order. So if you get into this, there's this book by Coxell O'Shea, the undergraduate textbook. So the test, whether you've understood it, is lexicographic says that the high variable is so expensive that it makes its monomials more expensive. Reverse lex says the cheapest monomial is so cheap that it makes its monomials the cheapest. And they're not the same. Okay? They're, in fact, very different. So those are the term orders. Now, once you have a term order, then every polynomial has a leading term. Okay, that's clear, right? So, because they are totally ordered, right? There's the highest monomial and the next highest monomial, and we write them in this order, and the leading monomial is called the initial monomial, and is denoted by in of f, but it depends on the term order. So it's in sub term order of f. That's the initial monomial. Now that's a basic concept. That's the pivot in solving linear equations. The symbol for differential operators, right? If you talk about that, we just spent an hour talking about differential operators. People talk about the symbol, right? So you have some operator and the highest guy, that's the symbol. And same concept. Here we call it the initial monomial. Now, if you have an ideal, if you have a system of equations, we code as an ideal in the polynomial ring, then there's the initial ideal, and that's defined as follows. So the initial ideal is the ideal generated by all infinitely many initial monomials in of f, where little f runs over all infinitely many polynomials in the ideal I. Emphasis on infinitely many, right? So because you're given a finite system of polynomials now, but in the initial ideal, it's not enough to just look at the leading terms of what you're given, right? Because you're given these operators, right? They have some symbols, but there might be some hidden, implied, inferred relations that you don't yet see that has some other leading term. And that you have to take into account. Okay? So the initial ideal in of I, according to this definition, is generated by infinitely many monomials, namely the leading monomials for each of the infinitely many polynomials, little f, in the ideal I. Okay, so here's the definition. So a finite subset, blue G, of an ideal I is said to be a Gröbner basis with respect to the given term order. So you and I have agreed on some term order. So let's agree on the degree lexicographic term order or something. So we've agreed on one of these term orders. So once we fix that, then we say a finite subset of an ideal is a Gröbner basis if the finitely many leading monomials in G of the finitely many polynomials G in G are enough to generate the initial ideal. Okay, let's prove a theorem. Okay, so theorem, every ideal has a finite Gröbner basis. Okay, proof, well, look at the ideal of leading monomials in of I by Hilbert's basis theorem, right? It's finally generated by a finite subset of monomials, say 17 of them. Now those 17 monomials, they are leading terms of some blue guys, right? So take those 17 blue guys, they form a Gröbner basis, end of proof. Okay? So we've just proved that every ideal in a polynomial ring with respect to any term order has a finite Gröbner basis. Now, the term basis on this slide and in this theory is extremely unfortunate. Because when you hear basis in mathematics, you sort of think it's minimal in some sense, right? So a basis of a vector space, right, that sort of spans the vector space, but it's also linearly independent. It's small, right? So, and the way we've defined it here, it's not at all minimal. So there are many generating sets, so we can add. So the way I've defined it, it should be really called a Gröbner generating set or Gröbner spanning set, right? Because you can throw in more polynomials and more and more and more, and you still satisfy this property. But that's just for historical reasons. So this is just how the term was defined, and that's what it's called. But so basis in this sense, there's no minimality yet. There will be minimality on the next slide. So to fix this, there's the notion of reduced Gröbner basis. And there are three requirements. So let's state first the theorem. So the theorem says if we fix an ideal I in the polynomial ring and a term order, then there is a unique reduced Gröbner basis for the ideal. And the three ways to make it reduced and unique is first, rule one. So first of all, you make every polynomial monic, right? So you have these polynomials, they have some leading terms, but these leading terms can have coefficients, such as 13. Now, since 13, for me, unlike for Brandy, is not 0, I can divide by 13. I'm just kidding. I can divide by 13, and then the leading term is 1 times a monomial plus stuff, and I do that. Okay? Now, secondly, I'm going to throw out wasteful, irredundant polynomials. So I require that the set of leading monomials actually minimally generates the initial ideal. So if there's somebody I don't need, I'm going to just throw them out. No questions asked. And the third rule is called, no trailing term of little g and big G lies in the initial ideal. So I have now my bag of polynomials. So a trailing term is some term further down the road that's not a leading term. So if a trailing term of some polynomial is a multiple of the leading term of some other polynomial, well, then I can make progress, right? Because then I can multiply that leading term by something and subtract it from the other one and keep going. Okay? Now, you know this, of course, from linear algebra. When you do Gaussian elimination, right, so what do? In Gaussian elimination, so you have some matrix, right? So, you do row operations, and then after a while, you get this, right? Sometimes you're done, right? That's the Gröbner basis. But you're not at reduced Gröbner basis yet because, the trailing term of this trailing guy coincides with this leading guy, right? So this sort of trailing thing in the first row still coincides, so you have to go further, right? So that's called whatever something something until you have something that looks like a unit matrix. So this is the input, that's the Gröbner base, that's the reduced Gröbner basis. So suppose you walk out of this lecture hall and somebody asks you, what's Gaussian elimination? What should the answer be? Well, it's Gröbner basis for linear polynomials, of course. Okay, so that's the reduced Gröbner basis. So let me talk a little bit about geometry. So in algebraic geometry, we study the zero sets of polynomials, and they look like this. So these are surfaces, points, curves, things like that are specified by polynomials. So if f is a set of polynomials, then its zero set or variety is the set of all vectors z1 up to zn. And here I like the coordinates to be complex numbers, such that f of z1 up to zn is 0 for all f and f. Okay? Now, that's it. That's the varieties. The set of all complex solutions to the given system of equations. Now, the given equations, those I write down, and they have rational coefficients. Now, the points and the variety, I just think about them. I don't write them. I can't write them down. You can write them down, but I can think about them. I can sort of think about all these points, but I'm not going to write them down. It's just easier to work over the complex numbers because they're an algebraically closed field. Right? So the fundamental theorem of algebra says that every polynomial in one variable has a complex solution, and that just makes things a little easier over the real numbers, or let alone the rational numbers. Now notice that if you have, two sets of polynomials and they generate the same ideal, well, then they have the same variety, right? Because if I have a bunch of polynomials and you throw in some polynomial linear combination, that's not going to change the solution set. It's going to vanish exactly where the old guys vanished before. So the variety depends only on the ideal. In particular, if blue G is the Gröbner basis for the input brown F, then they have the same variety. So having the same ideal implies having the same variety. Why is it called a variety? Sometimes in the olden people called it a manifold, but then manifold took on a different meaning. So manifold are not supposed to have corners, I don't know why it's called variety. It's called variety. Okay. These things are called ideals and varieties, Yeah. Okay. Here's another theorem. So this is the Nullstellensatz, sort of like Fahrvergnügen, those long German words. So the Nullstellensatz, the theorem of the zeros, proved in 1890 in the same paper by the same guy, says the following. If you give me any system of polynomial equations, brown f, then I can tell you whether or not not your system of equations has a complex solution, whether or not your variety is zero, is empty. Namely, your variety is empty if and only if the unique reduced Gröbner basis that you see on your screen after you open your laptop consists of the singleton 1. Okay, so if Mary Lee writes down for me 20 algebraic equations in 10 unknowns and says, gee, I wonder whether there are any solutions, then I take her brown polynomials and I produce the blue output, and if it's 1, then there's no solution. Right? Now, the if direction is trivial, right? Because if the output is 1, we know that the variety of f is the same as the variety of g, but if g contains the monomial 1, right, so that has no zeros. Right? So the 1 polynomial, there's no place where the 1 polynomial is 0. Right? So therefore, the if direction is trivial, so the content is the only if direction. Example, let's say Mary Lee's polynomials are these 3 Brown equations in 2 unknowns x and y, and I ask myself, do they have a common solution? Well, I type them, you type them into Macaulay 2, you hit the button, out comes g is 1, so there are no common solutions. However, if I perform a change, if I take the middle input polynomial and I replace the constant term minus 25 by minus 26, then the unique reduced Gröbner basis consists of 2 equations, x minus 2 and y minus 3, and by inspection, I conclude that the variety consists of a single point with coordinates x equals 2 and y equals 3. Okay, so that's Hilbert's Nullstellensatz. Now, Hilbert didn't phrase it this way, but that's really the content of Hilbert's Nullstellensatz. It says the variety is empty if and only if the Gröbner basis is the singleton 1. Well, that's good. So now we know how to test whether or not a system of equations has a solution at all. So let's suppose the answer comes back that it's not 1. Okay, so we run this, and the answer comes back, there are solutions. Okay? So what's the next question you would ask? So we give some system of equations, and the answer is there are some solutions. So what question would you ask next? What are they? How many, right? So how many, right? So there are some, but how many are there? So that's the next slide. How many, right? So to answer that, we need the notion of a standard monomial, conveniently introduced by Anne this morning. But let me go over it again. So I is any ideal, and we agreed on a term order, then a monomial, x to the a, is called standard if it's not in the initial ideal. So a monomial is a standard monomial if it's not a multiple of any of the finitely many blue leading monomials that you see on your screen after having run Macaulay 2. And we call it a standard monomial if it's not in the initial ideal. Right? So here, these are the columns that have exactly 1, 1, and the rest zeros. They're called standard. So those are the sort of dependent variables. I'm sorry, the other ones. Those are the non-standard ones. So for example, if n is 3 and the initial ideal is x1 cubed, x2 to the 4th, and x3 to the 5th, then the number of standard monomials is 60. I lose a slide. And then if the initial ideal were x1 cubed, x2 to the 4th, and then x1, xq to the 4th, then the number of standard monomials is infinite, right? So the number of standard monomials could be finite or infinite. In the second case, it's infinite because every power of x3 is infinite. It is standard, it's not in the ideal, right? So there's the number of standard monomials, and it could be finite or infinite, and you can read it off by looking at the leading terms. Great. Here's the fundamental theorem of algebra. The fundamental theorem of algebra, in my reinterpretation, says the number of standard monomials equals the number of solutions. The answer to your question is it's the number of standard monomials, right? So the number of zeros in the variety, the cardinality of the variety, equals the number of standard monomials, counting multiplicity. Now, in one variable, you knew that, right? So if you have, in one variable, you have a polynomial of degree d, then the fundamental theorem of algebra says it has d complex solutions, but you have to count multiplicity. Okay? That's called the fundamental theorem of algebra. And that's true, right? Why is it true? Let's prove it, right? So if we have a polynomial of degree d in one variable, so what are the standard monomials, right? They are 1, x, x squared, up to x to the d minus 1, and then you're in the initial ideal. So there are d standard monomials, so therefore there are d roots. Question?
What does multiplicity mean?
Ooh, what does multiplicity mean? In one variable, you know what multiplicity means, right? No? Okay. So multiplicity no, it's okay. We can. So suppose I have, a polynomial like this in one variable. So this has two roots, right? There's an incredibly complicated formula that has to do with the square root of, So there's a formula that people memorize that expresses x in terms of a and b. But it says somewhere plus minus square root, right? It could happen, if you're very, very unlucky, it could happen that, that thing under the square root becomes 0, in which case there's only one root. But really, to be graceful, we'd like to call this guy having multiplicity too. So the multiplicity is sort of a number up there. And there's a way to say it too in this case, but maybe I don't have enough time. Okay? So example, if we take this brown set of polynomials, we run a pure-lex Gröbner basis, we look at the leading terms, they are the underlined terms, they're the leading terms, then we can see that every power of z is standard, right? So you can see that none of the underlined terms is a pure power in z, so therefore there are infinitely many solutions. On the other hand, if we make a small change, if we take the first input equation, x squared z minus y, and we replace it by x squared z minus 1, then we get a different reduced Gröbner basis. Now the leading terms are x, y squared, and z squared. So there are only 4 standard monomials. 4 is a finite number, so we conclude that there are 4 solutions. Okay, so that was the answer to your question. So suppose we run this, and we're in the first case. Namely, there are infinitely many solutions. What's the next question? Mary-Lee gives me her equations. We run this for a while, and we see there are infinitely many solutions. So what should you ask next? Cody, what would you ask next? You're cheating, right? You have this thing in front. So what's the next question? We have some system of equations, and there are infinitely many solutions. So what question should we ask now? What are the basic solutions? What are the ones we're most interested in? Suppose we're in 3 space, and I give you a bunch of equations, and we have some solutions, So. Okay, well, what I had in mind is the dimension, right? There's sort of a fundamental difference. So either you have a bunch of points, or you have a thing called a curve, or you have a surface. Right? That's sort of the next invariant that I was thinking is the dimension. Maybe that was implied when you say basic solution. I guess you're thinking about linear space. If you have linear equations, then you can write down a basis for the solution, for the, and the cardinality of that basis is called the dimension. But here, the equations are nonlinear. So nonlinear algebraic equations, just like nonlinear differential equations, have a solution set that is not a linear space, but has more complicated structure, but nonetheless it has a dimension. And that we can, so what's a dimension, right? So a curve, this thing has dimension 1, right? And then the blackboard has dimension 2, and This lecture hall has dimension 3. Right? So we have a very intuitive idea of what dimension is, and that we can compute too. So here we go. So the dimension of variety is computed as follows. So let S be a subset of the variables, x1 up to xn. And I'm interested in those subsets which have the property that no monomials in these variables are in the initial ideal. Or another way of saying it, I'm interested in subsets of the variables such that every monomial in those variables is standard. Right? So we have 10 variables, and maybe there are 3 of them such that every monomial in those 3 is standard. But there might be another 4 somewhere else such that every 4 in those is standard. And in theorem, the dimension of the variety, the intuitive dimension, is equal to the largest cardinality of such a subset of variables. Now it's good to think back about Gaussian elimination. Right? So the dimension is the number of non-underlined variables in Gaussian elimination. Same thing. Okay? So that's the largest cardinality of any subset of variables such that the monomials in those variables are all standard, and that's the dimension. And now we can ask all these other questions, like what are the interesting ones? Are there singular solutions? Do they have real coordinates? What kind of coordinates do they have? So now you can keep going. You can ask more complicated questions, and then, if we had a couple more hours, which we don't, then there would be similar expressions to address some of those questions. Question? What do people think? Does it depend on the ordering? It's a miracle. Right? That's incredible, right? This S, these sets S that run for competition, they depend on the ordering. But the left-hand side doesn't depend on the ordering. Doesn't depend on the ordering. Same here in the counting business, right? So this, in the fundamental theorem of algebra, right? The particular set of standard monomials, that will depend on the ordering, right? So, okay, let's do an example. So suppose we want to solve one linear equation, right? So suppose we're interested in the solution set, of this equation. Well, the solution set of this equation in the plane has dimension 1. It's called a line, right? So, well, if this is the leading monomial, then y is standard, and there's exactly, then if this is the leading monomial, then the powers of y are the standard monomials, right? But, if this is the leading monomial, then the powers of x. That depends on, what we call the leading term. But the set of standard, the cardinality of the set of standard monomials and the structure of the dimension, that's independent. But that's a miracle. Okay, blah, blah, blah. Yeah, I said that ideals are sort of like normal subgroups, right? So the factor structure is called the residue ring. So theorem, the set of standard monomials is a Q basis for the residue ring. Now Q is really the rational number, so modulo the ideal. So every polynomial f can be written uniquely as a Q linear combination of standard monomials. Given any polynomial, there's an algorithm, the division algorithm, that produces this representation, and it's called the normal form, and you've enjoyed doing this, where you had not just one polynomial, but you did it at the same time for n polynomials and n unknowns. And you enjoyed looking at and biologically interpreting the structure of those n normal form polynomials. So that's called the normal form. And algebraically, the standard monomials, they form a Q vector space basis, or in Brandy's case, an F sub 2 vector space basis for the residue. Now, let me wrap up. Now, since these Gröbner bases are so amazing, how can you compute them, right? And how can you test whether you have one? So maybe we don't want to compute that NP complete. They're hard to compute, terrible, Let's ask an easier question. Suppose somebody walks in to the room with a bag of polynomials and claims that they are a Gröbner basis. How can I call him a liar? How can I test whether he is right or not? Okay? So that goes as follows. I take any two polynomials, g and g prime, in the bag, And I formed the so-called S polynomial. It's a subtraction polynomial, m prime g minus mg prime. So the S polynomial is the stingiest linear combination that knocks out the leading term. Right? So I have two polynomials. The first guy has a leading term, and the second guy has a leading term. And I want to force a cancellation of leading terms. And you do the stingiest thing you can, and that's called the S polynomial. Okay? S for stingy. Theorem, called Buchberger's criterion. The bag of polynomials that just walked into the room is a Gröbner basis if and only if every S pair, every S polynomial formed by two guys in the bag has normal form 0 with respect, upon reduction with respect to the given bag. So I don't, in the definition of Gröbner basis, there was this sort of infinite test. I underlined the adjective infinite. But in this test, I only need to have finitely many tests, right? So if, there are 10 polynomials, I only have to make 45 checks, right? Because there are 45 pairs out of 10 polynomials. Here's the algorithm. So given a finite list of Brown polynomials, I like to calculate the reduced Gröbner basis for the ideal they generate. Step 1. Are they already a Gröbner basis? Well, that would be nice, but I know how to test it, right? So if that's yes, I'm done. I'm going home. And that's polynomial time, right? That 45 tests, right? And then if no in step 3, then we have to do something. Then we pick a pair. Then we found a witness, right? Then if the answer was no, then there was one of these stingy pairs that didn't reduce to 0. Now, since it didn't reduce to 0, we just take it and we throw it into the bag, and we do it again. That's the whole algorithm, right? Now, if this terminates ever, right, then we reach step 4, and then we do the auto reduction. So then make it monic, and we throw out, unnecessary guys and so on, and we get the reduced Gröbner basis. So the only question is, why does this terminate? Why does this loop always terminate? And the answer is, again, the Hilbert basis theorem. Because the Hilbert basis theorem says equivalently, there is no infinite ascending chain of ideals. So whenever we have one of these witnesses, its leading term was not divisible by anything that's in the bag already. Otherwise, we would have reduced it further. So if we throw it in, the current tentative proposed initial ideal grows and grows and grows. But if you have ideals that keep growing, at some point they terminate. Okay? So that's why the algorithm terminates. And I don't derive any bound from this argument, but there are better ones that give you bounds. A simple example, two polynomials in one variable, right? So suppose you leave this room and somebody asks you, what is the Euclidean algorithm? Answer is very simple. It's Gröbner basis in one variable. Right? So the Buchberger algorithm in one variable, that's the definition. The Euclidean algorithm, so let's do it. So we have x squared plus stuff. We have x cubed plus stuff. We knock out the leading term by the stingiest possible way. So we take x times the quadratic polynomial minus 1 times the cubic polynomial, and we get 3x squared plus x minus 4. The x squared is still divided by something underlined. We reduce once, and we get to minus x8 plus 8. That's not 0. We throw it in, we do it again, and then we're done. So the new set turns out to be a Gröbner basis, but then we have to make it reduced, right? So now we have the cubic, the quadratic, and the linear. So we throw out the quadratic. It doesn't contribute to the initial ideal. We throw out the cubic. It doesn't contribute to the initial ideal. Then we look at minus 8x plus 8. We divide by minus 8 because we're not in characteristic 2, right? And we get x plus 1, and that's x minus 1, and that is the unique reduced Gröbner basis. Summary. Gröbner bases and the Buchberger algorithm are fundamental in algebra, and I mean undergraduate algebra. In China, I would mean high school algebra. Okay? Gröbner bases are fundamental for high school algebra. And in fact, you know them already, right? So as soon as you write down, terms and the first and the second, you keep canceling, that's what you've done all along. You've done Gröbner. In France, you did Gröbner bases a long time ago. As soon as you solve linear equations. In fact, there are only two kinds of mathematicians, right? There are the mathematicians who, use Gröbner bases, and then there are the mathematicians who use Gröbner bases but don't know about it yet. They have many applications, such as this workshop. There are more advanced questions you can ask. So how do these solutions look like? So once you take graduate classes in algebra, then you ask questions like, what's the cohomology of the solution set? Are there corners? Are there singular points? Can we study and resolve these singularities and then, try it today? And thanks for your attention.